Let us discuss this sample space. What is sample space? Whenever we are doing a random experiment, that means this phenomena we are repeating in our lab, we know that all the outcomes of this phenomena. That random experiment whenever we are doing, all possible outcomes of a phenomena or random phenomena or random experiment, we say all possible outcomes of a random phenomena or random experiment, it is called the sample space. For example, if you are tossing a coin, suppose we denote that random experiment by this abbreviation RE. Suppose the random experiment, it is tossing a coin. So, what are the possible outcomes of this random experiment? It may be head or tail. These are the possible outcomes. All possible outcomes of this random experiment, it is known as sample space. Let us consider another random experiment. Suppose this is random experiment. Second example, suppose throwing a die or rolling a die. Suppose you are rolling a die, then what are the possible outcomes? S is equal to all possible outcomes. Suppose you are denote the sample space S1 here, sample space S2. This is the set of all possible outcomes 1, 2, 3, 4, 5 and 6. It seems like sample space contains always finite number of elements. This is like abstract, these are not real number, head and tail, these are some integer values. It may take any real numbers also, it may not be discrete. For example, let us consider the random experiment lifetime of a electronics group. Suppose it is transistor. So, lifetime of a electronics goods, or you can consider very simple bulb, suppose lifetime of a electronics goods. So, lifetimes means we are measuring, suppose you consider one bulb and we want to see how many years or how many hours in some units. It is actually, if you consider properly time is a continuous variable, it may be any point in the real line, but we can make suppose hour or minute, then it will be discretization. But if you consider theoretically, it will be any time in the real line, it may last. So, we will see that how many times, how much time t it is actually working. So, after that it fails. So, this sample space it can be represented as by a real number t, such that see that initially if you buy the bulb and then just immediately it is not working, then the lifetime will be 0. So, it is possible that theoretically it may be 0, otherwise it is greater than 0. And we do not know how long it will continue. We do not know is there any maximum limit that it can be working, it can work, other more than m it is not possible, we do not know that much value. So, that is why theoretically we write that this is t is the time, lifetime of a bulb, it is t belongs to the real number such that t is greater than equal to 0 and less than infinity. So, here the sample space it is uncountably. So, we know that countable set and uncountable set. So, countable set means any set, if you have a subset of a natural number, A is a subset of a natural number means you know that the set of natural number we denote by 1, 2, 3 like this. A is a subset of natural number. If you have a 1 correspondence, so A may be whole natural number also, all set of natural number. If you have a bijective correspondence from G A to some this set S, then S is known as, so G is 1 1, or we say that 1 1. If there is any 1 1 correspondence to A to S, it has to be 1 2 also, or in other way we can say that if there is a 1 1 corresponding to S to A is a subset of a natural number, either it may be whole natural number or it is a subset of a natural number. If there is a 1 1 correspondence S to A, or there is a bijective also, if you consider. So, if you consider S to A and A is a subset of natural number, if there is a G is 1 1 function exists, then S is known as countable set. It may be infinite. So, for example, natural number itself is a countable because 1 goes to 1, it is a bijective function and 1 1. And if you consider Q is a set of rational number, that means all the element it can be represented by P by Q form, Q not equal to 0, P and Q are integers. Then this is also note that Z natural number J set of integers like containing 0, 1, 2, minus 1, minus 2 like this, negative and positive number including 0. This is there is also 1 1 correspondence between Z and natural number. So, similarly, Q also we can we know that it is there is a 1 1 correspondence between Q and set of natural number. If it is a finite number, it is also a countable number because you can give, because A is a subset of the natural number. So, you can take this subset and then you can show that just a identity map, it is a 1 1 corresponding from the set to the subset of the natural number. So, this is also a countable set. So, these are all countable set, but whenever we cannot represent, we do not have this kind of 1 1 correspondence between the set to that subset of natural number, then it is uncountable set. For example, set of real numbers. So, real number is nothing but rational union all the irrational numbers. So, now even if you consider this interval 0 to 1, so in the real line you consider all the points in between 0 to 1, this is a uncountable set. So, 0 to infinity, this is also a uncountable set. So, sample space may be countable set, sample space may be uncountable set also, it may be finite, it may be countably infinite, or it may be uncountably infinite. So, this is the sample space. Next, we will discuss one of the important topic, that is known as an event. So, what is event? That is because later on we will discuss probability of a event. So, that is why it should be understood very clearly that many times we just say, for as a layman, it is nothing but a subset of a sample space. So, if S is a discrete, you can consider all subsets of the set, it is nothing but the event, we discuss event. So, here it is any subset of the sample space S is called the event. Even whenever S is a discrete set, then S, this is the Venn diagram, A is the event. So, for example, if you consider the random experiment, first random experiment, tossing a coin, then in this experiment the sample space S1 contain head and tail. So, what are the subsets we can consider? Subset are one subset like head, another subset like tail, null set also subset of S, S itself also considered as a subset of S. So, containing all these subsets, all subset of S. So, note that if it is a finite set, then all subsets we can count. If the set number of elements in S is suppose n, then we say it is called a power set. So, we denote like suppose it is like a script A. Power set is nothing but all subsets. So, the power set, we say power set A is defined by the set of all subsets of S. If you consider set of all subset of S, it is known as power set. If number of elements in S is n, then the number of, so note that this notation just we for simplify for a short type of writing, we say it is a number of elements in the power set is 2 to the power n. So, here you can see that S1 it is containing only 2 elements, then the power set contains all the subsets of S, it contains 1, 2, 3, 4, 2 to the power of square 4 elements. So, this is the relationship with power set and the set, finite set. If it is infinite, then 2 to the power infinite, it is not a number. So, then we cannot say that. But if S is countable, then the power set also will be countable. But if S is uncountable, so then this power set we cannot say that it is countable. If it is infinite set and then it is this power set, if you consider, so it will be huge. So, that is we represent by some cardinal number. So, this cardinal number we say that. So, same we are saying that suppose this there is a notation that eta is a cardinal number of a natural number, then all the sets having same cardinal number, that will be like a countable set, that is a 1-1 correspondence. Whenever there is no 1-1 correspondence, like there is no from that set to natural number, there is no 1-1 correspondence. So, then we represent that like set of real number, this cardinal number we represent by, it is just a notation, the 2 to the power of eta, more some to understand it is a bigger set, because infinite set we cannot just compare by the number of elements. Finite set we can compare, like this set is bigger than this set because it contains 4 elements, this contains only 2 elements, we can compare. But infinite set, so when the set of natural number, it also infinite set of rational number, it is also infinite set, we cannot compare because both are infinite. So, but by some bijective correspondence, by some concept of 1-1 mapping like that, so we can have some kind of concept that eta is a cardinal number of natural number, all countable sets should have like same cardinal number, there would be, because there is a 1-1 correspondence with natural number. And then whenever we will go to uncountable number, like set of rational number, set of real numbers, it has countable, this has a cardinal number 2 to the power eta. These are some of the concept, it is not that much required here. So, we will discuss the related things. Event is a subset of a sample space. So, it is a event, this is also a event. So, we say A, this is a event, B is a also subset of a sample space, it is event. So, let us discuss another example. Random experiment is suppose second example, this is rolling a die. So, then our sample space content 1, 2, 3, 4, 5, 3, 4, 5 and 6. So, here this power set of S2, this will contain many subsets. So, 2 to the power of 6. So, some of the subsets suppose I am representing here, maybe 1, maybe 2, maybe 1, 2, 3, maybe 2, 4, 6, 1, 3, 5, 3, 6, some of the subsets. Suppose let us consider these subsets. A is equal to 2, 4, 6. It is a subset of A2, subset of S, it belongs to A2 power set. So, this is it is nothing but all the even numbers. So, when we say that this even occur, so we are throwing a die and we observe that because only one observation it will come out of all the possible outcomes. It will not observe all the point in a event. one observation. So, suppose S is a observation in S2. So, this S is equal to suppose 2, only 2 observed. 2 means it is a even number. Now, if this S belongs to the set, the subset of S that we are considering, then we say that, say A is occurred or A is observed. A is happened, we can say. So, that means the event A happened or A is the event A is happened. So, whenever we see that, because whenever you see that 2 observed, then 2 is belongs to A, then A is observed. So, 4 also, for 4 also A is observed, for B 6 also A is occurred. So, now if you see that S is equal to 1, suppose it is happened. So, but you are throwing a die and you see that in the top face of the die is 1, S does not belongs to A. So, A is not occurred. So, we say that the event does not occur. So, that is the some concept that how event we define. And now, if you consider the third random experiment, this random experiment is nothing but lifetime of a measuring the lifetime of a electronics goods like bulb. Now, in that case, what is the sample space? This is equal to all t belongs to the real number, t is greater than equal to 0, less than infinity. It is a uncountable set. In that case, if you consider the power set, that means all subset of S3, there will be a problem. So, researcher or scientific communities, so they found that whenever they try to discuss that all subsets of S3, if you consider as the event like power set A3, all subsets of S3, then we will face problem defining probability. So, in a broader sense, like in a advanced probability, you may learn that is called a measure theory. So, in the measure theory, if you define measure, so here we will define the probability on the subsets like events. Then whenever it is an uncountable set, if it is a countable set or discrete set, then this is okay, you consider all power set. But if it is an uncountable set, we cannot consider power set. If you consider power set, then you cannot define the probability. It will be there will be some it will not be well defined. So, there will be some contradiction, it can be shown, but we will not go through in that direction. We will just understand that whenever it is not discrete, the set is continuous, uncountable set, we need to define some special subsets, not the all subsets. We have to consider a class of subsets of S, the sample space, that is known as some name it is given, it is called a sigma field. So, that all the elements inside that sigma field known as events, not the all subsets. So, that what is the definition? First, we will discuss the definition of field. What is the definition of a field? So, let S be a non-empty set. A class C of subsets of S is called a field if it contains S itself and is closed under the formation of complements and finites in them. So, field is defined like that. Let S be a non-empty set. A field of S is a class of subsets of S, that means it is a collection of, so it is it is a class C of subset of S. A field of S is a class C, it is denoted as C, subsets of Fs satisfying this the following conditions. So, a class C of subsets of S satisfying the following conditions. So, what are those conditions? One is that S will be belongs to C. Second is that if A is a subset such that A belongs to C, implies the complement also belongs to C. See that A complement belongs to C. And third condition is that if A1, A2 all are A1, A2 belongs to C, that means both are subset, implies A1 union A2 belongs to C. So, finite union it will be, so it is known as field. So, now basically important is that we need to know sigma field. Sigma field is just a extra one condition that it is required. Sigma field is not, it is not nothing but whatever it is field, it has to be field. Not only that, this what this condition was that it is finite union, here it is a countable union. So, we will discuss some of the example. So, what is sigma field? Sometimes it is known as Sigma-Algebra. Some of the books it mentioned Sigma-Algebra, some of the book you will find it is discussed as a sigma field. Sigma field is not, it is defined as let S be a non-empty set, a class C of collections of subsets of S. So, a class C of subsets of, actually I am just writing extra collections. So, class C of a class C of subsets of S is said to be sigma field, said to be if it satisfies the following, it satisfies the following conditions. So, what are the following conditions? So, whatever field those conditions, so this S also has to be in C. Second, if A belongs to C, implies A complement also belongs to C. And third property is, this is the extension of the field that is called sigma field. If the countable collection like this belongs to C, implies A1 union A2 union AN union like this. So, this is countable infinite collection of subset of S that is belongs to C. If it is belongs to C, that also this union also belongs to C. So, this is known as sigma field or Sigma-Algebra. Now, note that if it is a some collection some class of subsets of S, it is a sigma field, it will be a it must be a field also, because you can see that any finite union, suppose if you consider finite union, so then let us take the it will make it infinite. So, suppose I want to see that A1 A2 belongs to C, just then because the infinite collection, it is in the third property, it is saying that it belongs to C, let us consider this collection. So, this is an infinite collection like countable infinite, A1, A2, A3 is phi, A4 is phi. So, then this is nothing but just only A1 union A2, and now because of the third property in the sigma field, it is a infinite union, this must be belongs to C. So, hence for a finite union also A1 union we can see that belongs to C. So, this must be a field. Let us discuss some of the example. So, for example, suppose you consider suppose S is head and tail, suppose random variable random experiment we are considering. First example, tossing a coin. So, sorry, tossing a coin, the sample space S1 is nothing but head and tail. Suppose we do not want to, so whether power set will be a sigma field, because power set contains all the element, the complement S also belongs to the power set. Any subset you consider, their complement will be subset of S, and that is will be inside the power set, that will be a inside the S. And now if you consider some countable union, countable elements of the power set, that means those are subset of S. If you take the union of all our subsets, so it will be inside S. So, power set will be a sigma field, but we are not interested to power set, because if it is an uncountable set, S is an uncountable set, then power set will face difficulties to define the probability. So, let us define some of the sigma field that is not a power set. So, let us consider, suppose you consider here it is just A is nothing but H. Now, just I want to check one collection, just it contain this S1 and A, whether it will be a sigma field. See that it belongs to S1. So, first condition is satisfied, S1 is belongs to C. Second condition is that A belongs to C, A complement has to belongs to C, but A complement is nothing but tail. So, A is not inside C. So, then it is not a sigma field. Hence, what we will do to make it sigma field, we will what we will do, we will add some of the sets inside. So, let us take the union of the A complement also. So, that is nothing but the tail, sorry, this is the tail, union of tail also. Then our set become also S1 complement phi also, here we include phi is always there. So, then our C become nothing but here, in this case it become again power set. So, this is nothing but head, then tail, then this is S1, head, tail, then phi. So, then if you include all this set, then you can see that it is a sigma field, because A belongs to C, then A complement is tail, this belongs to C. You take any element, because countable here only 4 elements. So, only finite things we have to check, then you can make it union of other like a phi. So, then for any infinite collection also this is true. For any, if you have, if you make it in an infinite collection, adding some sets like phi like this. So, then you can see that this will be in the C. So, this will be a sigma field, but it is a power set, again it is coming. But what we did this kind of operation, like whenever it is not a sigma field. So, what we are doing? We are adding some of the sets to make it sigma fields. So, subset of S to make it sigma field. This kind of process, it is known as sigma field generated by the set. So, we will take a collection. So, let us consider second example, random experiment. Suppose this S2, so this is throwing a die. So, in that case S2 contain 1, 2, 3, 4, 5 and 6. Now, let us consider A is nothing but 1 and 2, and okay, suppose B is nothing but 3 and 4 and C is nothing but 5 and 6. if you take this collection, so here C is there, so we take a different notation. Suppose F is the class of subset of S2 containing S2 itself A, B and C. Let us see that whether it will be a sigma field. So, condition 1, S2 belongs to F, condition 2. So, it is important. So, A is 1, 2. So, A complement will be 3, 4, 5, 6. So, this is not there. So, what we will do? We will add this set. So, this is not a sigma field. First of all, A, suppose 1, 2, A belongs to C, F, but we see that A complement does not belongs to this collection F. Hence, F is not a sigma field. F is not a sigma field. So, then what we will do? We denote that, suppose then we just say that this is suppose a set S dash here, S is nothing but all this collection like it is A, S2, let us take another notation here, okay, S dash is okay I think, S2, A, B and C, this is a set, it is not a sigma field, we found that. We denote this. So, this is nothing but the notion is that sigma field, okay, sigma field generated by this set by S dash. So, what is that? You include many more other sets, those it is required. So, what will be the sigma S dash? Now, S2, A, B, C, they are union, B union C, A union C and they are complement also, that means A complement intersection B complement, because by de Moivre's law A union B complement is A complement, union B complement, B complement intersection C complement, A complement intersection C complement, like this. You include many more sets, so that, and then if you take the union also you are considering A union B union C is nothing but S2. So, you will see that after that it will be a sigma field. So, this is called a sigma field generated by set S. Now, let us consider the third example, the random experiment. This is example 3. This is random experiment is nothing but lifetime of a, measuring the lifetime of a bulb. So, lifetime of a bulb if you consider, then what will be the our sample space? This is T belongs to real number such that T is greater than 0, less than infinity. Now, let us consider one set is like that, this is 0 to 1, this set. Now, we want to find the sigma field, because only considering this set, suppose your C is nothing but only A, it contains only this subset. So, it is a subset of S3 obviously. Now, if C is equal to A, only it is contains only this set A, will it be a sigma field? It will not be sigma field, because A complement is nothing but 1 to infinity, it will not be a sigma field. We will consider a sigma field generated by C. So, this is C. So, this is the sigma field generated by C. So, let us denote by C sigma. So, what will be the set? So, because it has to be a sigma field, that is why S through has to be inside here, A is already there, then because complement also will be has to be there and the null set is there. Now, you can see that this is a, so you can add more sets also, so that it will be a sigma field, but we want to add that many of sets, that is becoming just a sigma field. So, it is called a smallest sigma field generated by C, this set C. So, because it will be a sigma field, because if you consider S3 is belongs to C sigma, second condition is that A belongs to, for any element A complement, then A complement is A. So, that is why any element A belongs to C sigma implies A complement belongs to C sigma. If you take union, this is nothing but S3. If you take intersection, this is nothing but phi, all belongs to the sigma field. So, any collection also if you consider, because there are only finite number of elements. So, that is why any for any collection A1, A2, An. So, if you, because to make it infinite you have to repeat phi, and A1, A2 you take one of the sets, then union of ai I is equal to 1 to infinity, this countable selection collection also will be inside C. So, this will be a sigma field. So, this is some kind of concept of sigma field we discussed. So, this is required whenever we will define the probability, this sigma field concept it will be required. That is why we discussed it. You may go through in detail, some of the books also we refer. So, there you can find more details about this sigma field and some of the examples we discussed. So, please go through it and you see that whether you have understood, you get the clarity. Now, next we will discuss how these events are defined, because this is a subset of a sample space. So, some of the set operations we have to know. So, that is very important, some of union, intersection. So, maybe you have already learned those things, since these are